Right. So we've got to the point of comparing the expressive power of fixed point logic with polynomial time. Everything expressible in fixed point logic is decidable in polynomial time. On ordered structures, everything decidable in polynomial time is expressible in fixed point logic. But fixed point logic by itself, in general, without the assumption of an order, is too weak to express all properties in P. And in fact, there's trivial properties in P which are not definable in fixed point logic. And this is the example which I mentioned in the context of first order logic, simply saying that the number of elements in the structure is even, for example. Now I'm going to talk about how we would prove that and develop the tools which are going to lead us on to further investigation. We do this by considering fragments of first order logic, right? So now we're going to something rather weaker. Fragment of first order logic defined by limiting the number of variables. So we write LK for the collection of those first order formulas which use only the variables x1 through xk, though the same variable, of course, may appear bound in repeatedly in several different places. So we're not limiting the number of quantifiers or anything like that. We write this equivalence relation, equivalence superscript LK, to denote for a pair of structures, AB, and a tuple of at most k elements in A and in B, that any formula of LK which is true of one, true of this tuple A in the structure A, for example, is also true of the other, right? So this tuple in this structure cannot be distinguished from the tuple B in structure B by any formula of LK. That's what this equivalence relation denotes. Now, if I take a formula which has k variables altogether, including a tuple of free first order variables, and it also has a free second order variable. So this formula defines an operator, as we've seen, which then defines a sequence of relations. It turns out that each of these relations is definable uniformly, independently of the structure, by a formula of first order logic using no more than 2k variables. So right, for each one, there's a formula phi m. For each m, I should say, there's a formula phi m, which in any structure A defines the relation phi, you get phi m plus, you get by iterating the operator defined by phi m plus 1 times. And this formula has no more than 2k variables altogether, and therefore the number of variables is independent of m and independent of the size of the structure. I'm not going to run through a proof of this, not in the lecture anyway. It's a proof by induction using substitution and renaming of bound variables. I'll say that much. So the idea is that you inductively, you have a formula for phi m, and you get a formula for this by substituting that formula for phi m in phi for all occurrences of the relational variable r, and you have to rename variables to avoid capture. But once you have 2k variables, you're not creating any subformulas with more free variables than that, and a renaming of variables will suffice. I'll leave the details as an exercise. As an example, graph connectivity is axiomatizable in LK. Note, this is not definable in first order logic. So no single sentence of first order logic defines connectivity. But you can define an infinite collection of sentences which axiomatizes connectivity. And this infinite collection has a constant bound on the number of variables. Any constant bigger than 3 will do. On the other hand, the property of having an even number of elements in the universe is not axiomatizable in LK for any constant k. And essentially, this thing I alluded to over here, the fact that you can define any stage of unfolding of the fixed point operator using a constant number of variables means that anything that is not axiomatizable with a fixed number of variables is not definable in fixed point logic. But I'll say a little bit more about that in a moment. First, let's consider as an example, here's an axiomatization of connectivity in using just 4 variables. You can get away with 3, but I think it's a bit simpler if I do it with 4. So here's a formula I write. For any natural number L, this formula says there's a path from x to y of length at most L. And this is really the unfolding of my transitive closure formula up to L steps. How do I say there's a path from x to y? Well, I say there is a z1, such that there's an edge from x to z1. And now I say there is a z2 with an edge from z1 to z2. Let me just say this. I'm trying to say that there's a path from x to y, right? And I could say this. If I wasn't concerned about limiting the total number of variables, I could just say use L variables to say there exists Z1 up to ZL, or ZL minus 1 in this case, with an edge from x to Z1 and edge from Z1 to Z2, etc. But instead, I am saying there's a Z1 with an edge from x to Z1 and a Z2 with an edge from Z1 to Z2. And then I just reuse the variable Z1 by saying there's a Z1 with an edge from Z2 to Z1, etc. I reuse the variable Z1 and Z2 repeatedly. And at the end, I say there's an edge from Zi to y. I is either 1 or 2, depending upon whether L is odd or even. Okay. Strictly speaking, I wanted less than or equal to L. So at each of these, I should also have the disjunction x is equal to Z1, right? Or here Z1 is equal to Z2. Either there's an edge or they're equal. And that will give me all x and y such that there's a path of length at most L. And the point is, apart from x and y, I just use the 2 variables, Z1 and Z2, and nothing else. So now I can write down a formula which says that the graph is disconnected. So I can't write down a single first order formula that says the graph is disconnected. We know you can't do graph connectivity in first order logic. But for any constant L, I'm writing down the formula which says that whenever there's a path of length at most L plus 1, there's already a path of length at most L. So this is saying that the longest simple path in the graph is of length at most L. And there is a pair of vertices for which there's no path of length at most L. So this whole thing is saying that the graph is disconnected, and whenever there is a path, there is one of length at most L. So again, for each L, I have such a formula. And the total number of variables in this formula is independent of L. It is at most 4. It is 4. X, Y, Z1, and Z2 are the only variables used anywhere in this formula. Now, how do I say that a graph is connected with an infinite collection of sentences? Well, basically, I take the negation of disconnect L for all possible values of L. That's an infinite collection of sentences. And any graph that satisfies all of them must be connected. Any finite graph that satisfies all of them must be connected. Okay, so I have axiomatized connectivity using just 4 variables. And I haven't said this, but essentially anything that can be defined in fixed point logic, for any property that's definable in fixed point logic, there is some constant k such that that class can be axiomatized by a collection of first order sentences, possibly infinite, using no more than k variables. Okay, and that follows from the unfolding of fixed points I described previously. Now I'm going to get on to the tool. I'm ultimately leading to proving that certain properties are not first order definable. Sorry, not fixed point definable. And to do this, I want to show that they are not axiomatizable using k variables for any constant k. And the tool here is the Pebble Game. It's played on a pair of structures A and B using by two players. We call them spoiler and duplicator, using k pairs of pebbles. So think of the game this way. The game board is A and B. The pebbles are the tokens which are moved by the players. Spoiler is trying to demonstrate a difference between the two structures, and duplicator is trying to pretend that the two structures are the same. The game proceeds in rounds as follows. Spoiler moves by picking a pebble and placing it on an element. A pebble AI on an element of A, or a pebble BI on an element of B. Right? So spoiler chooses one of the pairs and places either the B pebble in the pair on an element of B or the A pebble of the pair on an element of A. Duplicator has to take the other pebble in the pair and places it on an element of the other structure. Now, at any point, there are some pebbled points on each structure, and this defines a partial map from A to B, right? The map that takes the element pebbled by AI to the element pebbled by BI. If this map is not a partial isomorphism, right? If there is some atomic fact true in one of the structures and false in the other on pebbled elements, then spoiler has won the game. Spoiler has demonstrated the difference between the two structures. And the key theorem is, if duplicator has a winning strategy for Q rounds of this game, then A and B agree on all sentences of LK of quantifier rank at most Q. Okay. So there is the K, the number of pebbles, corresponds to the total number of variables. The number of rounds of the games corresponds to the quantifier rank, and a duplicator winning strategy for K pebbles and Q moves. Q might be much bigger than K. So if Q is much bigger than K, then during the course of the game, you have to remove pebbles from one place and possibly move them to another. And so A and B are not distinguished by any sentence of LK if duplicator has a winning strategy for every Q, which on finite structures is the same as saying that duplicator has a strategy to play forever, right? This is because if duplicator has a winning strategy for every finite Q, then you can pick a value of Q which is bigger than the larger of the two structures raised to the power K, which means that duplicator has a winning strategy which forces a repeat of the game position, and which is sufficient for duplicator to have a strategy to play forever. So in general, we just say that duplicator wins if duplicator has a strategy for playing forever. Okay, and then we don't care about the quantifier rank. And if that's true, then A and B cannot be distinguished not only by any sentence of LK, but even by any infinite collection of sentences of LK. So to show that evenness is not definable in fixed point logic, it suffices to show that for every K, there are structures AK and BK. One of them has an even number of elements, the other has an odd number of elements, and they are indistinguishable in LK. In other words, duplicator has a winning strategy for playing the K Pebble game forever on this pair of structures, right? The argument being that if evenness were definable in fixed point logic, then there would be a constant K such that there was an infinite collection of sentences of LK which defined evenness. But then this AK and BK, one of them has an even number and the other has an odd number, would be distinguished by this sentence contradicting this. Okay. So why is this? Well, this is actually quite easy to show, because if I take K elements, if AK has K elements and BK, well, at least for K even, you can let A have K elements and B have K plus 1 elements. If K is odd, let AK have K plus 1 elements and BK have K elements. Either way, AK has an even number of elements, BK has an odd number of elements, and both sets are of size at least K. and they have no other relations on them, or all relations in the vocabulary are empty, if you will, then whenever duplicator plays on an element, spoiler plays on an element, duplicator responds in the other structure. If spoiler plays over here, duplicator responds over here. And all duplicator has to do is ensure that when two pebbles are placed on the same element, they're on the same element over there. And whenever a pebble is placed on a different element, it's placed on a different element over here. There are only k pebbles, and there are more than k elements, or at least k elements on each side. So there's always somewhere that duplicator can play, and this allows duplicator to play forever. That's all there is to it. Okay? So evenness is not definable in fixed point logic. Here's a simple proof that the property of having a perfect matching is not definable in fixed point logic. Take, for any k, this graph, which is the complete bipartite graph on two sets of k vertices. This is a complete bipartite graph with k vertices on the left, k plus 1 vertices on the right. This one has a perfect matching. This one clearly doesn't, right? But now again, duplicator has an obvious winning strategy. Whenever spoiler plays on an element over here, choose an element over here. Whenever spoiler plays on an element on the right, choose an element on the right. If spoiler plays over here, you play over here. The point is that whenever two elements are on opposite sides of this bipartition, there's an edge between them. Whenever they're on the same side, there isn't, and that adjacency is preserved over here. And again, because there's at least k elements in each of these sets, duplicator can always choose an element on which to play. Okay, and this can carry on forever. With k pebbles, the position will always be a partial isomorphism. Okay. So the two graphs are LK equivalent. One has a perfect matching and the other doesn't. And this is for any value of k. We can construct such a pair of graphs. And therefore, the property of having a perfect matching cannot be defined with a fixed number of variables. And therefore, it cannot be defined in fixed point logic. It's also worth noting that the graph on the left has a Hamiltonian cycle, because you can start at any point, go across anywhere, go anywhere you haven't yet visited, and then return to the starting point. And that's a cycle. And obviously you can't do this on the right because each edge crosses from one side to the other. So the only way to visit every vertex and return to the starting point is by making an even number of crossings. But that means you can't have visited all the vertices because there's more on the right than there are on the left. Okay, so there's a Hamiltonian cycle on the left, but not on the right. So the same example also shows that the property of having a Hamiltonian cycle cannot be defined in fixed point logic. So, in fact, we have the following are not definable in fixed point logic. Evenness. This also can be shown by the same example that we just had on the previous slide. Perfect matching, Hamiltonicity. Now, all of these examples are shown. All of these involve some form of counting, right? The first example shows that in fixed point logic, we can't express simple counting properties. And really, the proof for perfect matching is really exploiting the fact that we can't count. We can't tell the difference between, a set of k vertices and a set of k plus 1 vertices to show that perfect matching is not expressible. So this led to the proposal many years ago by Neil Immerman that we should extend fixed point logic with a mechanism for counting, and maybe that's sufficient to then get all polynomial time properties. This leads to the logic we call fixed point logic with counting, or FPC, which is going to play a sort of central part in our explorations of symmetry in computation. So what is FPC? Well, we have fixed point logic, and we now allow two sorts of variables. So we have the usual variables which range over the domain of our structure, right? Whenever it's interpreted in a structure A, they range over the elements of A. And we have another sort of variable which ranges over non-negative integers. Okay. What connects the two is that whenever we have a formula with a free variable x, then we can form a term, hash x phi, or which we read as the number of x such that phi. And this is a numeric term. It denotes a number. It denotes the number of elements of the structure A that satisfy phi, or simply the number of the number of values for the variable x that satisfy phi. On number terms, so what's a number term? A number term is either one of these number variables or something like this. We allow our arithmetic operations like addition and multiplication. Okay. Now, if you have variables ranging over the non-negative integers and you can do arithmetic on them, then of course in principle you get huge expressive power because you have the full power of first order arithmetic. We don't want that. So we limit the quantification over number variables to be always bounded by a term, t, okay? Which really means that the interpretation of the range of numbers, I mean, with addition and multiplication, the only terms you can form are polynomials in your variables, which will be variables bound outside, or numeric terms, and these are limited by the size of the structure A. So effectively, what this means is that the range of every variable is bounded by some polynomial in the size of the structure, which is exactly what we want. Okay. Here's some examples. They're a little bit complicated to write out, but it'll kind of illustrate this syntax with an example. Here's a formula for writing down that a graph has an even number of edges. And this is something you cannot do in fixed point logic. It's an exercise. Why you can't do it? I mean, it's actually just simple adaptation of the perfect matching example we saw. So it's a little bit complicated to write out. In fact, in full, here it is. So let's see what it's saying. I will just decode this for you. I say there is a number which is bounded by this, which is simply the number of x such that x equals x. That's just the number of elements in the structure. Okay. In fact, I say nu1 is x equals x. So I really want a name for the number of elements in the structure, and I say by saying there is a nu1 bounded by this, which is equal to this. And then I say there's a nu2, which is at most nu1 times u1. So I've got a number which ranges up to the square of the number of elements of the structure. Okay. And what is nu2? Here's my defining expression for nu2. I say nu2, I really want nu2 to be, it's going to be twice the number of edges. And I do this by basically summing. I want to sum over all vertices of the degree of the vertex. Okay, so look at this. For each x, this is the number of vertices which are neighbors of x, right? The number of y such that exy. That's the number of neighbors of x. Now, for any mu, this expression, the number of x, number of y, exy equals mu, is the number of vertices which have degree mu. So I take the number of vertices of degree mu, multiply that by mu, and sum over all possible values of mu. Then I get basically the sum of the degrees of all the vertices. And the sum of degrees of all the vertices, of course, is exactly twice the number of edges. I want to say the number of edges is even. That's the same thing as saying that this nu2, which is twice the number of edges, is a multiple of 4. And that's what I say here. There is some nu3 less than or equal to nu2, which is, when multiplied by 4, gives you exactly nu2. Okay, so this says nu2 is a multiple of 4, and this says nu2 is the sum of the degrees of all the vertices. Now, I've written this sum, and how do I do that in the logic? Well, I do that with a fixed point. This is breaking down this expression of calculating the sum over all possible degrees of the number of vertices of that degree. Okay, here it is done as a fixed point expression. What is it doing? It's constructing inductively the collection of pairs, mu, tau, where mu is a number and tau is the sum so far of all vertices of degree at most mu. So you start off with mu being 0 and tau being all those vertices of degree 0. And then inductively, if mu is mu prime plus 1 and the number of vertices you have so far is tau prime, then you add to tau prime mu times this expression over here. And then at the end you say that nu1 and nu2 are in the fixed point of this. Okay, which is really to say that nu2 is exactly this sum. I'll leave you to examine this in detail yourself. Now, fixed point logic with counting, it might look like a sort of abstruse and in some sense arbitrary definition. I've taken first order logic, I've added inductive definitions, I've added a mechanism for counting, but it turns out it has many equivalent characterizations showing it's a robust class, and I will just mention one because we've seen this before. I talked briefly about relational machines, where the input is a relational database. You have relational and numerical registers with join, projection, complementation, counting. If you take this machine model and limit it to polynomial time, then the properties that are decidable by such machines are exactly those which are expressible in FPC. Okay. Now, FPC is a very expressive logic. It turns out that many properties which are sort of obviously polynomial time, you can just turn into FPC expressions. You know, they're like the property of having an even number of edges, you know, is obviously polynomial time, and the kind of obvious definition translates into FPC. And this already includes things which are, in some sense, as hard as they get inside P-complete problems, like the circuit value problem. You don't even need the counting for this. The circuit value problem, in case you don't know it, is you're given a circuit as an input that is a labeled direct acyclic graph, where the source labels are labeled by 0 or 1, and internal nodes are labeled by Boolean operators and or not, and you have to decide what is the value at the output gate. So you're given a circuit with all the inputs already given, and you have to just decide what it is. And this is actually sort of a simple induction, easily defined with a fixed point logic. You don't need counting. And you can decide whether the output is a 1 or a 0. If, along with and or and not, you allow either threshold or counting gates or majority gates, then you need the counting mechanism in fixed point with counting to express the problem, but it is still within FPC. There are many problems which are polynomial time, but not obviously polynomial time, in the sense it takes effort to show that there are polynomial time algorithms, which turn out to be an FPC. One of the most sort of comprehensive results along this line is Groe's monumental result that fixed point logic with counting captures all polynomial time properties on proper minor closed classes of graphs. If you don't know what these are, I'm not going to go into much more detail. I just wanted to flag this really important result. But on the other hand, there are properties which are in polynomial time and cannot be expressed in FPC. This was already established by Zeiführer and Immermann back in, the journal paper appeared in 1992. We're going to look at this construction in rather more detail. They define it as a class of graphs, which is a kind of, it's a complicated definition, as we'll see. But from this, many natural properties turn out to be not definable in FPC. You can prove this. So for instance, XOR SAT. This is the problem of satisfiability of Boolean formulas, which are expressed as conjunctions of literals connected by XOR. This is polynomial time because it reduces to solving a system of linear equations over the two-element field. And more generally, solving a system of equations over any finite field turns out cannot be expressed in FPC. And it turns out that by reductions, one can then show certain NP-complete problems are provably not in FPC. This includes SAT, Boolean, satisfiability of Boolean formulas, Hamiltonicity of graphs, three-colorability of graphs. None of these is in FPC. Hamiltonicity we saw already is not in fixed point logic. But what this is saying is, even if you add counting, we can prove it's not. Okay, we wouldn't expect it to be because everything in FPC is still in polynomial time. But this is the whole point, that irrespective of the P versus NP questions, we have categorically proofs that certain NP-complete problems are not in FPC. So what we're going to do next is develop the tools for showing such inexpressibility results in FPC. Before we do that, we'll take a short pause.